So welcome everybody. I'm now very honored to introduce Monte Bauman, a fan and a friend of the VM Workshop for a long time, and he's going to give us an update on some of the technology from a hardware perspective. So Monte, I'll turn it over to you.
Thank you, Bill. I do rather enjoy the ZVM Workshop. Always have. Love going to them when the calendar allows. And talking about hardware is one of my favorite things. So this is a fun topic for me and a fun forum for me. So I'm just going to jump in and tell the Z and LinuxONE server story, and start and it's a technical venture through the story. And I'm going to start with the core. And of course, we've been building cores in the Z space for quite some time, and they've gotten more and more and more interesting. And I'm going to kind of illustrate just how interesting they've gotten and how much engineering we do in this course such that it's a great Linux-oriented workload processor these days. We certainly have had a tried and true history of building Z chips. We've been at 5.2 gigahertz before. Twice. It's kind of an interesting story about how we yield more and more performance out of a cycle. So I'm going to illustrate and build on that story. So hopefully it'll be an interesting story. As you know, just in summary form, we have two form factors for the LinuxONE servers, and have for some time, similar to the IBM Z servers. We've got the mid-market servers, which we now sometimes call the single frame servers, the TO2 and LT2. Built from the very same chip as the high-end servers, which are the bigger multi-frame or potentially multi-frame systems. And we'll talk to that and how we build these servers and when a multi-frame system is required versus a single-frame system. But it's a quite varied and quite scalable and quite capable and flexible product line. In summary form, I'm going to kind of express and build out how this all comes to pass. But in summary form, this chart illustrates the TO1 or the LT1, LinuxONE LT1, multiple models, from one to well, this is the from 1 to 190 cores, up to 40 terabytes of memory, up to 5 motherboards, if you will. So very, very robust and scalable system. Scalable to the extent that I've heard a story told that if we ran all of Black Monday's transactions on one server in the world, and that one server could be this server, and this server, if you fully configured it to run all those transactions on Black Monday, would be about 5% busy. So very scalable, very powerful server, and it's got a little brother. The little brother is the TO2, or in the LinuxONE parlance, the LT2. And it's got the same core, the same architecture, the same capabilities, but just in a more commoditized form factor. A mid-market, a little easier to manufacture, a little easier to produce server, just has scaling attributes that are mid-market oriented. So I'm going to build out both of these systems, but I'm going to start with the core. I do invite questions along the way. Bill, you may have to read the discussion board for me. Since I'm in screen show mode, I can't see the discussion board. So somebody will have to interrupt me.
I will do that. I'll let you know if any questions come in.
Nice. So I'm going to start with a blank slate. So this is the Silicon budget. The Silicon engineers start with a blank slate. And first thing they're going to do, if it's a process, is they're going to design a pipeline. They're going to have a target for a frequency rate that they want to run this thing at, which comes back to the performance they want out of it. And it's got to implement an architecture. So there's going to be registers and instruction pointers in accord with the architecture that they're implementing. But one of the first things we did in the IBM Z chip that was really interesting in the pipeline was create an out-of-order execution capability. Intel can do this. I don't know that they do it nearly as well as we've done it. They haven't been doing it for nearly as long as we do it. And we'll see that as each Z chip has progressed, a lot of the performance improvements have come from the ability to run more instructions per clock cycle. And the trick to doing so is taking the instructions in the order that lets you run multiple instructions per clock cycle. The other trick is to have a lot of places to run instructions. So we in our chip have 27 execution units, which essentially, in very simplistic form, suggests there's 27 places to run an instruction and 27 instructions that could run per clock cycle. Now that's highly theoretical, not quite practical, but that's the idea. There's lots and lots of places to run instructions. And if you can take them in the right order by taking them out of order, you can optimize the number of instructions you execute per clock cycle. So, and that's called superscalar. The other trick to a chip is, and a pipeline design, is preventing stalls. So a pipeline wants to churn along, and the data needs to be where it needs to be when it wants to look at the data. The next instruction has to be there when it wants to look at the next instruction. So the pipeline is a lot of, we have to feed the pipeline with the instructions and data they need. Otherwise, the pipeline stalls and has to wait for data to be cached in or instructions to be fetched so that the pipeline can then continue processing. And no chip in the world works quite so hard as we work to prevent pipeline stalls. Very large caches, and even a very large translation look-aside buffer, because virtual address translation is going on all the time. And if you don't cache and keep handy the translations that you've done, then you're going to be stopping the pipeline so that you can execute the math, do an address translation, and then restart the pipeline. So not only do we have large caches for instructions and data, we have a very large cache for translation look-aside. Back to the execution units. We have multiple load store units, multiple fixed point units, multiple fixed point units. And as you may have remembered from your green cards, your yellow cards, your pink cards, whatever you came into the world of the mainframe, you might remember all the various cards, and you probably remember coding and an assembler if you're lucky. That was one of my first jobs, was coding and assembler, and I loved it. But you might remember that most of the instructions that are interesting fall into these categories: load store instructions, fixed point instructions, or branch instructions. And so it's awesome that there's multiple places that these instructions can be executed in the pipeline, simultaneously executed. And back to pipeline stall prevention. There's another cache that is just for the branches. So it's a branch history cache. We intelligently analyze branches as they've occurred. We manage the caches and what we keep in cache based upon where branches have been and where we think branches are going to go. It's fascinating reading to understand how we do branch prediction on this core, because when you think about it, nothing kills a pipeline worse than a branch instruction. And there's nothing more, there's hardly anything more prevalent than branch instructions. So the ability to handle branches systemically with optimization is a great thing. The other,
so Monte,
yeah,
we have a question here. Can you comment on penalty for data and instructions in a cache line?
Yeah, it's bad if this was, when we started Z10 and the high-speed pipelines, ZOS didn't watch really very carefully where DSECs were versus where CSECs were, and occasionally a CSEC and DSEC would land on the same, close enough in memory that they would appear in the same cache line. So when caches are loaded from memory, it's not a byte at a time, it's a group of bytes at a time. So if a group of bytes come into cache and they have some data and some instructions all in that same group, and if that instruction is talking to that data, or sometimes there's self-modifying instructions, there's crazy things that programmers can do, those would all confuse the processor, and the pipeline would have to kind of restart, and it could be a bad thing. A performance penalty could occur. So ZOS went through a modernization of, I don't know, 8 years. I bet ZVM did too, where they paid close attention to cache lines, paid close attention to CSECs and DSECs, and basically CSEC alignment. They would align every CSEC on a cache boundary so that the next CSEC would be on the next cache line boundary. So we basically had to reorganize our software to prevent those occurrences of data and instructions coming into the same cache line. Hopefully that makes sense and answers the question. And Bill, if you want to comment, I know ZOS went through a big effort on that. It was a big chore. And I got to think ZVM did much the same.
Yeah, so we were a little bit more cognizant of that separation to begin with, so we didn't have as much, but we continuously review how we're looking at that aspect, right? And making sure that we're separating things, read only versus things that are getting updated and so forth. So yeah, that's a significant thing.
Yes, absolutely. So continuing the story, the other aspect of awesomeness in a Z chip is SIMD, the single instruction multiple data. So this is basically vector units. If you've been in this business long enough, you might remember the vector facility in the old 600J machines from years ago. In a sense, it's back. And it's been back for about 3 generations of cores. But we keep putting more and more logic, more and more capability into the SIMD unit. We're even doing COBOL arithmetic now in the SIMD unit. So, and we're doing encryption capabilities, and some encryption elliptic curve cryptography is done inside the SIMD unit. So SIMD is great because now you can basically add a row of numbers to another row of numbers and create a result set that's a third row of numbers. You can also manipulate characters because characters are rows of things. So you can do character manipulation with the SIMD unit as well. The Java JIT guys were quick to take advantage of the SIMD capabilities, and Java performs much better now that it's got SIMD under the covers. So it's been a great addition to the instruction set and a great addition to the hardware. The other thing I added here was compression and encryption, the CPACF capability. So we dedicate circuitry to encryption acceleration and compression acceleration. So we've had Lev Zempel compression for a long time, and now we have some Huffman-based compression in the chipset. And we're going to see in a second, we've got ZLab compression acceleration and another part of the chipset. So we've dedicated circuitry, and it's kind of a common thing. We see where software is at, we see where software has trouble, and to the extent we can, we take those software troubles and encapsulate them into hardware to accelerate the software. So encryption was a path length explosion. So we solved some of that path length explosion by adding hardware assists. Compression, path length explosion. Well, how do you solve that? Again, you put hardware acceleration into place. We're going to see the same thing with sort as this chip life evolves. Sort is a very problematic software thing. So we've got hardware acceleration and sort that's on the table. So an awful lot of great circuitry has been in place to run, and you might suspect that with this pipeline and 27 places for this pipeline to park instructions, there's some unused circuitry in the normal pipeline. And that's what SMT2 is about. If we have not just one set of instructions running through that pipeline, but we have 2, that's what SMT2 is. And it's the same hardware, the same pipeline, the same set of circuitry, the same set of execution units. But now that pipeline is being asked to manage not just one instruction pointer, but 2. And it's got not just one set of registers, but 2. And SMT2 for IFLs, for zips, for system assist processors, we're running this mode, and we can get 25, 30, 35% more throughput out of the core for asking that pipeline to manage 2 threads versus 1. So it's a terrific addition to the capability. And then another piece of the core story has just been the number of instructions. We might think that the instruction set of the mainframe is old and tired, but that would be far, far from the truth, because each time we come out with a chip, we come out with I've seen it as low as 3 dozen. Often it's dozens and dozens of new instructions. So the hardware is alive and living. The architecture is alive and living. And one example is kind of an interesting one, and that is there was a storage instruction that did decimal arithmetic. And of course, a storage instruction has to read the first operand from storage, read the second operand from storage, do the arithmetic, and then write the result back to storage. And all those sort of operations, very expensive. And it's a long-lived instruction, not a great performer. So part of the SIMD unit, part of the reorganization of the hardware was to let's do that same arithmetic, but now let's use it in an RR instruction format or register format. And if you recompile it, you've now got a chip that supports that RR instruction. It'll start using it instead of that SS instruction, and you get some of these results that are alluded to on the big yellow bubble. Much faster performance for those kinds of applications that use those new instructions. And that's just one of many, many examples. So this is the summary of a core. So it's an awesome core, over 2,000 MIPS yielded by this core, workload acceleration, pipeline stall prevention, just great technology. And the coolest thing about that core is we put 12 of those on a chip. So the Z15 chip is quite the piece of work. It has another large set of cache. It's so large that it's ECC protected. You might remember ECC from server days. It was a big deal when servers started protecting their memory arrays with ECC circuitry, error correction and change circuitry. Today, caches on Z machines are so big that we now have selected and use ECC to protect our caches, and I think we're unique in the industry for doing that level of protection across our caches. And then on the chip, we had a little bit of circuitry allocated to another level of compression acceleration. So there's actually three things are done in this circuitry. One is the new ZLib-based enterprise data compression. You might remember in previous machines, you had to buy a card and put an IO page to do this acceleration. Now that same function's been embedded in each and every Z15 processor chip. The other two cool things that are in that circuitry are asynchronous data mover facility. If you remember ADNF, that's still in there. And what was the other? Oh, sort. So there's sort circuitry that's in there. We haven't been telling the sort story very much because the software has to come up to speed. But as soon as DF sort and the other sort products, sync sort and the others are up to speed and ready to release, there's going to be a big splash on sort capabilities that have been installed in the hardware. So it's quite the chip, 9.1 billion transistors, 12-core chip with huge cache, error protection, and then we take that chip and we've got to put it into a socket. So this is the drawer. The Z15 drawer is a 4-socket, 4-chip drawer. We add to that motherboard a storage control chip, which is another big set of cache as well as an interconnect chip. We'll see that how it interconnects as well as adds cache. And then the memory DIMM. So there's a bunch of memory that we add to the system in accordance with how much memory you want. And then we have the connectors from the processor motherboards to the IO drawers and other facilities in the system, for instance, Sysplex connectors if you're in a ZOS environment. So that motherboard is quite the piece of technology. And we use this motherboard in both of our product lines, the high-end LT1 product line and the LinuxONE or the TO1 product line in Z15 sense. We use the same drawer in the mid-market system as well. We'll see that. So this is kind of the illustration of how you take that motherboard, that processor drawer, and we can scale it up in the TO1, the LT1. So that if you want up to 34 processors, you could do that on a single drawer. If you need more, which we hope you do, you can. If you get up to 71 cores in out of a second processor drawer. A third processor drawer could be added in the LT1 or a fourth. Or if you want the maximum, the maximum capability, it's a 5-processor drawer built system that yields up to 190 cores and yields up to 40 terabytes of memory. So that scales, that core was about a 2,000 MIP core, if you remember right. But now when you get 190 cores put together and running in an SMP machine fabric, you get up to 200,000 or so MIPS of capacity out of a single server. So it's very scalable. If you're looking at the Z machine, it still has a sub-unis, but if it's a LinuxONE machine, every IFL runs at full speed and is SMT2 configurable if your workloads are amenable to SMT2 execution. The mid-market machine is just a little different. It's usually a single board system. So the first 4 models here are one drawer systems, the Max 04 to the Max 31. And the max number is the maximum number of cores available to you, the customer, to configure as IFLs in the LinuxONE system. So you can get up to 31 out of that single board, single motherboard, single drawer. But in this system, unlike the Rock Hopper 2, its predecessor, we can have a dual drawer system and basically double, I guess a little bit more than double, the capacity of the system by adding that second drawer and going to that Max 65 system. The memory's doubled on this system as well compared to its predecessor, which had a maximum of 8 terabytes. This guy has a maximum of 16 terabytes. So a nice increment to the technology capability as we move from the Rock Hopper 2 to this, the LinuxONE 3 LT2. So it's kind of interesting how these systems are built. So I'm going to go through the packaging real quick, hopefully pretty quick. So this is the LT2 packaging scenario. So it starts with that 19-inch rack, and then you install a processor drawer. It's not much fun without a processor drawer. It's not much fun if you can't do I/O to it too. So let's start with a processor drawer and I/O drawer, and they would fit in the bottom of the rack as kind of illustrated with my simple PowerPoint rendition. If you wanted to add I/O, that's fine. You can non-disruptively plug in another I/O drawer, non-disruptively plug in additional I/O cards, and keep running without even an outage as you scale up your I/O capabilities. Up to 3, up to even 4 drawers. There's a little caveat on the 4 drawers. The Max 4 only has enough socket connections to drive 3 I/O drawers. But the rest of them, the Max 13, 21, and 31, can scale up to connecting to 4 drawers worth of I/O. These are the same drawers as in the high-end product, the LT1. So same cards by and large in the mid-market servers and on the high-end server. I shouldn't have said by and large. It is the same card. The Max 65, and this is kind of the second rendition of this story. If you think or you know you need to get to that Max 65 config, which is to say anything above 31, is it 31? Anything above 31 cores, you're going to want to either plan ahead and reserve space for that second processor drawer, or just buy the Max 65 from the get-go, which is probably the best way to go. You should all buy a Max 65. But if you can't quite write that check, you can reserve space for that second drawer, put in the first drawer, put in the I/O drawer, and the feature code to reserve that space just for that eventuality that you're going to grow. That says to the second I/O drawer, hey, I can't be put in the bottom of the rack, just above the processor drawer. I got to leave space, so I'm going to put my second I/O drawer up yonder. And then maybe you go to that processor drawer. You take that reserve space and install the second processor drawer. It is an outage to do this, but it's not a terrible outage. You slide in that second processor drawer. Later, you might add a third I/O drawer. And this illustrates, because of the packaging, that a Max 65, because we're doing 2 processor drawers, can only have 3 I/O drawers. So kind of a little trade-off between processing capacity, I/O capacity that you have to work through. Now, I'm going to shift to the high-end product. You saw in that LT2, we never moved beyond a single frame, a single rack. And now we're going to get into multi-rack scenarios, because that's exactly what the LT1 or the TL1 product line is, a multi-rack. And it starts again with a single rack. And we're going to put a processor on the bottom. And you see now we've got the radiator. So I could have or should have mentioned earlier, I didn't, but I could have, should have, that the high-end product at 5.2 gigahertz needs to be actively cooled technology. We need to run fluid, in this case water, across those processor chips to remove actively that heat with fluid so that those chips stay within a nice thermal envelope of long-term happy execution capability. Just like your car, it's an internal radiator. This isn't a water-cooled system in the sense that your car is not water-cooled, which is to say you don't plug a hose to it. It's an internal water-cooled system. Same thing here. The next thing we might do is add an IO drawer. And again, the IO drawer can be added non-disruptively. It is Gen 4 connections between the processor drawer and the IO drawer. Actually, it's Gen 4 in the processor drawer, and it's fanned out across multiple Gen 3s to the IO drawers. And which is part of the magic behind how we can connect so many IO drawers, as you're going to see here in a second. A single drawer and a single rack of the LT1, you can see we can get 3 IO drawers. And if we need to go to more IO, then that's okay. We can non-disruptively add and connect a second rack, add non-disruptively and connect more IO drawers, and get up to 8. Add another, rinse and repeat, another rack, another set of IO drawers. You can see we max out at 12 IO drawers. And this would be a kind of an odd configuration to have a single processor drawer and that many IO drawers, but it's a valid and illustrative configuration for our purposes here. More common would be a similar idea that we saw before, where you're going to install a single processor drawer with the notion that you're in all likelihood going to grow or want the ability to grow. So again, you can reserve in that first rack the ability to add additional processor drawers. For having those reserved spaces in the config, then your IO drawers, of course, move to places that are outside of the purview of those reserved spaces. And then when you start to scale your IO, you're going to be adding a rack and your IO drawers much more readily. Along the way, you can add that second processor drawer, add some more IO, add the third processor drawer, and now we've maxed out another config. This time we maxed out at 11 drawers, not 12 of IO, but we've got 3 processor drawers. And this was all field upgradable. The bulk of it was non-disruptively field upgradable. The processor drawer upgrades are not non-disruptive, but the rack and IO drawers are non-disruptive. So we can get from A to, from one CP to I think it's 71 CPs, all in this kind of configuration. The next comment about the LT1 or the TO1 is, if you know you're going to be in need of a 4 or 5 drawer system, you actually can't get there from a single drawer system. You have to get from the factory that 4 drawer or that 5 drawer system, which is say we cannot in the field upgrade, we cannot in the field, I guess upgrade's the right word, upgrade you from a 3 drawer processor drawer system to a 4 drawer or 5 drawer processor drawer system. It's just too complex and install to do in the field. So if you know you're going to be big and you want to be big, and you're going to be a 4 or 5 drawer system, you need to start that way. So you would start with this config. You would add your IO drawers on top of that. You might add IO. And this is where you get to a 4, and this is the maximum physical footprint of the machine, would be a 4 rack system. So again, now we're back to 12 IO drawers at max. We're up to the 5 processor drawers at max. And this is basically a full-blown end-to-end system, that 190 core, 40 terabyte configuration. Now, this is all based on IPDU technology, which is the power, Intelligent Power Distribution Unit. And IPDUs, the equipment for IPDUs just slides into the side of the racks. It's down the rack sides here. It really doesn't take space in terms of the U units of the racks. It's all kind of integrated into the racks themselves. So IPDU is intelligent. It's very efficient. It's the preferred way to go these days. There's still kind of 2 things that might drive you to using the old-fashioned bulk power assembly power, which looks like this. You see that the bulk power assembly power units take up space in the rack. They take up much more space because they do more. One of the reasons you would do bulk power assembly is if you have basically dirty cords, dirty power coming off the grid. Either it's phase shifted or voltage wavers. I don't think we see this much in the United States anymore, but if you've got power issues on the grid, or if you've got the need for water cooling units, see down there at the bottom, the blue is not just radiator now, it's WCU, water cooling. So if you want to actually not use a radiator, just internal chilling loop, like I explained before, but you really want to use water that comes from outside the machine, goes up into the machine, and then leaves the machine, goes outside to the big chiller, and then comes back in. If you want to use classic water cooling in the old sense, that requires you to put the water cooling unit feature code on the system, and it requires you to use bulk power assembly. So those are the two sorts of conditions that typically drive you to bulk power. But once you're in bulk power, you can scale quite readily, as I'm illustrating now. But you the one thing you can't quite get to is 12 I/O drawers. You can only get to 11. It's typically not going to be an issue, I don't think, but there is that one that caveat to go into bulk power. So that's kind of the physical topology, and this is what it really looks like outside of PowerPoint, inside the real design. So that's kind of my story on the physicals of the hardware, and I'm going to segue now to the virtual construction of the system, but I'll pause and build checkpoint with you. Did anybody ask a question along the way there for the hardware?
So I don't see any additional questions. There was a comment about processor drawer 2 being added concurrently.
No, when you add a processor drawer, it is not a concurrent add. It's an outage.
Okay.
Once you have multiple processor drawers, you can do concurrent repair, kind of the old concurrent drawer repair stuff that we've done for years. So as soon as you've got multiple drawers installed, you can do some concurrent repair and upgrade kinds of things. But the actual installation of a processor drawer is an outage situation.
All right, got it. Thank you.
So segueing to virtualization story a bit. So some of this is review for the many of you who have been around this platform for a while, but I wanted to just illustrate a few of the new virtualization capabilities. So I'm starting with a simple chart that says this is the server at the bottom, whether that's an LT1 or an LT2. You've got Prism in the middle, and you've got a virtual machine at the top, and that could be a RHEL, SLES, Ubuntu, or ClefOS kind of virtual machine. Oops, wrong key. And you can have multiples of those, right? And this would be the case where those are hardware, what do you call them? Bare metal servers. Basically, those are LPARs. And we'll see in a moment how you might choose between LPAR hosted virtual instances of Linux or hypervisor hosted instances of Linux. So ZVM is our tried and true forte of our workshop. So ZVM's been around a great deal of time, and it's an excellent hypervisor, and it's an excellent place to run just many copies of ZVM. Excuse me, many copies of Linux. KVM though is a choice these days, and we're seeing KVM's adoption increase a bit. And this drawing is actually accurate. We can run ZVM on the left, we can run KVM on the right, we can run bare metal Linux in the middle. Very flexible virtualization structure of the system. And reasons you might do those or make those choices is obviously the LPAR limitation. Basically single digits of LPARs and then many digits of virtualization on top of our very robust hypervisors like ZVM and KVM. So depending on the shape of your workload, the horizontal nature of your workloads, or the vertical nature of your workloads, you basically choose and can readily choose bare metal or hypervised configurations. Of course, it's awesome that we have virtual networking capabilities. We've got vSwitch with ZVM. I'm sure there's going to be additional topics on that excellent technology, vNICs and vSwitches. KVM has similar networking. And through the middle of Prism, we've got virtual networking with hypersockets and with SMCD and SMCR, which are emerging Rocky-based technologies to improve and offload IP stack processing to the cards and simplify communications and more efficient processing. As you all know, I think, we can drive disk and storage with either of the traditional fabrics of count key data disk, which is ZOS style, old mainframe style connectivity through FICON, or we can enjoy SAN fixed block disk architectures as well through a FICON card configured as a fiber channel protocol card, or as I put here, for the non-Z crowd, they know what an HBA is. The Z guys might not know what that is. That's a host bus adapter. And that's the term more commonly used in the non-mainframe world for the connection between the connector in a server to a storage device, a host bus adapter. I'm illustrating here that we can actually, in a LinuxONE server, drive a 32 gig host bus adapter fiber channel protocol card. And it's unique to the LinuxONE servers. We can't actually put that card in the Z servers, which is interesting. So to enjoy the latest ISP fiber channel protocol, we can get to that 32 gigabyte per second form factor. Now I'm switching to the software, to the workloads. And what we're seeing in the world today around the workloads is kind of three classes of workloads. We're seeing a lot of integration and messaging workloads. We're seeing a lot of database, data and IO-oriented workloads. And we're seeing a lot of application service workloads. And we're seeing, the mixture that you're seeing here is the mixture we're really seeing between ISV or commercial software like Oracle and DB2, and MQ and WebSphere, and open source software. We're seeing, I think, a growing prevalence and growing ratio, if you will, of use of open source versus ISV or commercial software. So we're seeing more and more Postgres, Mongo, Elasticsearch, Kafka, JBoss, and so the flexibility of our system again is appropriate to the needs of the modern enterprise, in that they're using so much software from so wide a variety of sources. I tried to draw this picture illustrative too of the fact that there's occasions and needs of bare metal uses of servers and workloads. It's pretty often the case that those are driven by like large Oracle databases. There's many companies that choose to run a small number of large Oracle databases on bare metal. So we kind of illustrated that here. You can do that. On the other hand, small application servers, it doesn't make much sense to run those as bare metal. Those are much more often run as virtual machines on top of ZVM or on top of KVM, messaging much the same. So small horizontal stateless workloads are great fits for the hypervised ZVM hosted virtual machines. But there's occasions too where bare metal might make sense. And then we've got the additions of the last 2 quarters, I guess, 2.5 quarters, 2 quarters. So we acquired Red Hat. IBM acquired Red Hat late last year, and a lot has happened in this space as Red Hat has been revamped and reorganized to better I want to say to better treat LinuxONE and IBM Z. So they've done a nice job of refactoring their products, refactoring their strategies to be more cognizant of the IBM Z chip, to be more cognizant of LinuxONE Z and LinuxONE. So the whole Cloud Pak story is coming to LinuxONE Z. It's not all there yet. I've drawn it, and I don't want to. I guess maybe I should have drawn it a little bit better, because I'm alluding to the fact that it's all coming to LinuxONE Z. What's available now is the Cloud Pak for apps. Shortly, it was stated, before year end, I've been given the expectation that all the Cloud Paks, except for the Cloud Pak for security, will be available on LinuxONE Z by year end. And the Cloud Pak for security, I've been given to believe will follow early in 2021, at least in the first half. So these Cloud Paks will appear first on x86, but once they appear on LinuxONE Z, they'll be synchronized, and then they'll basically be a single drop of release, single release stream, and a very concurrent release path thereafter. So if you're not familiar with OpenShift, it's Kubernetes-based technology, which to a lot of mainframe folks, if you remember what, if you think about CICS and MRO and terminal owning regions and file owning regions and application owning regions, Kubernetes is much the same architecturally. Kubernetes has master nodes and worker nodes, and it's all about clustering and managing and distributing and controlling work in a sophisticated fashion to be available, to be workload manageable, and in a lot of ways, what Kubernetes has learned over time is what we in the mainframe have been doing for years with CICS, with IMS, even with WebSphere MD, with our server regions and control regions. A lot of the stuff we've learned, we're going to see as you look at under the covers of Kubernetes, which is what's under the covers of OpenShift. You're going to see those structures. So in a lot of ways, it's nothing terribly remarkable about it, except for the fact that it's multi-platform eventually, multi-architecture eventually, multi-language eventually. So the promise and the roadmap is really very, very interesting. And what's awesome is that the LinuxONE Z, even the ZOS, ZCX, LinuxONE, LinuxONE Z, we're right in the middle of this whole evolution of software and of OpenShift, and I think it's exciting. Partly because it's where development is going. So if you guys in the organizations aren't already looking at containers and container-based application development, container image repositories, container image-based construction of your applications, I'd be surprised. I'm almost sure that every organization out there is working towards that end. And just like IBM Software Group is working towards that end. So IBM Software Group itself is working towards building and managing our software and our middleware in image formats and building from images, delivering within images. And that indeed is what Cloud Paks are. It's image-based, container image-based delivery of software. Now, once you get to container, yeah.
A quick question in the chat was, is KVM hypervisor compatible with KVM on x86? Compatible in the sense of user experience / user space tools.
Oh, okay. I believe so. I mean, KVM is KVM. KVM is not an IBM thing. KVM is an open source thing, and KVM is a open source multi-platform. So I believe. There's always the dotting the I's and crossing the T's. There's always little gotchas and gitches, but by and large, I think the easy answer to that question is yes, KVM is KVM, just like Linux is Linux.
Okay, thank you.
Okay. So the last piece of this story of virtualization is the evolution of LPARs into secure service containers, and sometimes these are called secure enclaves now. So if you hear this term secure enclave, you've probably heard the term secure service container. What we're referring to with either of those terms is a special LPAR, an LPAR, kind of a hardened, battened down LPAR that is managed a little bit differently, configured a little bit differently, and the difference is in how we secure the innards, the contents of that container, shielding it from administrative layers. So no super users, no ability for an administrator to poke at an address space, poke at a process. One great example is, gosh, I forget which Bitcoin exchange or which digital coin exchange it was, but one of the one-off digital exchanges, it wasn't Bitcoin, but one of the one-offs got hacked for $500 million. So that was a big hack. And the way they did it was really clever. An administrator abended a user space. He dumped the user space. He looked at the dump and found the keys for that user. Then he restarted the user, subsumed that user's credentials, and pulled that money and now he owns that money. So it's kind of an interesting hack, an administrator hack, and that's exactly what Secure Service Container and Secure Enclaves protects against, is that type of hack, an administrator deep knowledge capability to intervene and introspect a system. Of course, with Secure Enclaves, since they're LPAR based, you're kind of limited to the LPAR bounds of the machine, which is 85 LPARs on the high-end servers, the LT1, 40 maximum Secure Enclaves or LPARs on the mid-range servers. So 40 is a decent number, 85 is twice that, but that's still not a huge number. So we came along with a second bit of technology, and this is really new. This just came out a month or two ago, and that's the secure, scalable, secure execution environment, which is basically a hardening and administrator proofing, much the same conceptually as a secure enclave, but we're building that capability higher into the stack. So it's built above the KVM kernel, built above the KVM virtualization capabilities. So it's a KVM based capability today, and it lets you scale up and scale out the number of instances of secure containers for software and systems. So it's very new, but we have high hopes that it's going to be a really interesting technology going forward. So the last piece of this story, as we get to the last, this is probably a good place to end this story. There's a bit of fun that I have with equations, and if you're like me and come from engineering, you remember that you know when your math is right when all the units cancel. So these equations are kind of fun and interesting to think about. And to a presenter, this is kind of my checklist. Did I talk about this? Did I talk about that? So when you guys get this deck, you can see it, and it's kind of interesting. But I did want to share this. This one's kind of an interesting chart. When you look at the evolution of our chips from the Z10 clear up here to the Z15, it's kind of interesting to see how many MIPS we're getting out of a keck. So back in the Z10, we were 43,000 MIPS. And now with the Z15, we're 306. So just great progress against the technology. But part of that secret is how much we do how much work per clock cycle. So we're doing for each clock cycle 547 units of work per clock cycle on the Z15. It was only 225 units of work on the Z10. So that's an indicator of how much better out-of-order execution is, how much better the superscalar nature of the system and a Z15 sense is than it was on the Z10. So it's kind of interesting that we went from 4.4 gigahertz to 5.2 gigahertz, which is what, 20% in clock time. But we're many times that in terms of capacity. And there's an energy thing. How many of you out here are not green? I think everybody has green at the back of their minds, being more energy efficient, being kinder to the planet. And this is an illustrative of how much kinder to the planet a Z15 is by looking at how much work we do per watt of energy, per kilowatt of energy. So we're doing like 10,000 units of work, MIPS, of execution per kilowatt on a Z15. It was only 1,500 MIPS per kilowatt of energy on the Z10. So that's just hugely more efficient use of energy on the Z15 compared to the Z10. So it's just kind of interesting. If you're Moore's Law kind of guy, this chart shows how we have up to the Z15, we almost exactly met Moore's Law. Now, Moore's Law breaks down going forward because we basically are at the end of physics. Atoms have not gotten smaller. We're basically to the end of atoms. We're counting the atoms that separate the circuits in our chips these days. So the aspects of Moore's Law will continue to be achieved, but not at the rate suggested by the Moore's Law of old. But nonetheless, it was a great story, and illustrative of that story is this data. So there's a few charts at the end of this deck that talk to encryption and some other special sauce features. But I think I got to the bulk of the message that we wanted to get to here. And I think this is probably a good place to conclude. Any final questions?
So I don't see anything else in the chat. There's been some great discussion there, but no additional questions for you.
All right. So that's my story, and I'm sticking to it.
All right. Well, thank you very much, Monty. Hopefully we'll get to see you face to face next year.
Indeed.
So, thank you.
Thanks, Bill.